My name is Toni Antonucci, and I'm very happy to welcome you all to the ISSBD pandemic keynote addresses. I really am very thrilled to welcome you, and I can see from the participants that we literally have people from all around the world. For me, in the United States, in the Eastern time zone, it's early morning, but we have people in Europe where it's afternoon, and people in Asia where it's evening. We have people in Africa. I think it's afternoon in Africa. I don't know if we have Australia represented, but we have usually. And so it's wonderful that we've managed to get so many people. We have India, Kenya, etc. So welcome to you all. We thought these pandemic keynotes would be a small token, a small gift to you, because we are very disappointed that we are not meeting in Rhodes. The meeting in Rhodes was completely planned. The program was all set. We were about to press the button on the printing the program. So it was one of the largest meetings we ever had, and we were very much looking forward to it. I had been there. It's a gorgeous place, let me tell you. The island itself is gorgeous, and the hotel was quite lovely, very different from our usual academic conferences. So our next meeting will be 2022, God willing, and we are speaking with the same folks at Rhodes about arranging it, though we haven't finalized it yet. We haven't signed the contract, but it's looking pretty good. Let me say a few words about how we will arrange this. We will have our keynote address for between 30 and 40 minutes. And then after that, we will have questions. Everybody is silent, is on mute as you enter as participants. And then if you have a question you'd like to ask, please send it to us in the chat box. And I will relay the messages unless Angelo reads them himself. Okay, we will treat the two keynotes separately. So we will end this one on the hour, and then we will move on to Dr. Akiyama, who I see is on as well. Welcome, Dr. Akiyama. You're mute, so you can't say anything. All right, let me just go right into a very short biography of Dr. Angelo Cangelosi, who is currently a professor of machine learning and robotics at the University of Manchester. He is also a Turing Fellow at the Alan Turing Institute of London and a visiting professor at the University of Milan in the Developmental Psychology program. His research interests are in developmental robotics, language grounding, human-robot interaction and trust, and robot companions for health and social care. I must say, I don't want to read the whole long introduction, but I do think this is such an exciting area, and I'm looking very much forward to hearing what you have to say about this, because I too have worked with our Robotics Institute. We have a newly formed Robotics Institute at the University of Michigan. So welcome and thank you. I turn it over to you, Angelo.
Thank you, Toni. Thanks for the kind introduction. And also I would like to thank Frosso, Antonella, and the other organizers of the event. Of course, we look forward to being there in 2 years' time, but it's a great opportunity to continue our scientific activities via these Zoom-like presentations. This talk is really going to be almost like a primer in developmental robotics, but to avoid this being a general developmental robotics introduction, I will normally contextualize the research around my own specific approach to the field. You will see it's mostly about language learning. And there is at the end some elements on modeling trust and theory of mind in baby robots. I am actually a psychologist. I trained at the University of Rome La Sapienza as an experimental psychologist, but then for my PhD and the last 25, 30 years, I've been playing the part of a computer scientist. But if I look at my approach to the field, there are really two questions that I always ask, general questions. One, as a computer scientist, how can I design robots that are capable of using language with humans, meaning sharing a common ground, common understanding of the meaning of words? And my talk will refer a lot about this shared understanding and grounding. And then as a psychologist, or sometimes I joke, as a former psychologist, then I would like to, sometimes at least, to relate my modeling, not only for building machines, but also for understanding natural cognition, human cognition, and in particular development. And you will see we achieved this at least in one of the models in which we worked. So this is a famous example from the philosophy of AI and cognitive science. Quine, the philosopher, uses the word gavagai in one of his papers and then in the book, 1960. And he says, let's imagine we are in the Amazon, we meet a new tribe, we don't know the language, we hear the sound gavagai when we anthropologists or we observers and the local people see a scene like this. So if I were to ask you in an interactive session, what do you think gavagai stands for? The majority of you would normally say rabbit, which is possibly right. Some people might say girl, some people might say green, grass, fur, ears. To be honest, all these answers are actually correct. It is only after a few trials of interaction and communication with the people that you refine the meaning of words. But language is indeterminate. It's hard to understand the meaning of words unless you go through repetitions and of course through a contextualized interaction. You know, if I say gavagai and I imitate the sound or the movement of a rabbit, you will probably confirm that the hypothesis about a rabbit. Now, this is not just a philosophical question. This is a real problem we had to go through as babies, because in our own languages, rabbit, coniglio in Italian, we would hear these words and we had to discover the meaning of words as babies. And this wasn't really straightforward, at least in the first instances. That's why we know in language acquisition, it takes a while for the child to acquire competence. At the beginning, just knowing few words. So how is this related to robotics or to AI and computer science in general? In principle, we shouldn't really worry anymore about building new models of language capabilities in machines, because we have systems like Siri, any other digital assistant system. Or if you really want to go to the history of AI, in 1966-67, Eliza was the first text-based chatbot that was able to communicate with humans. Eliza was actually meant to imitate a clinical psychologist. So this technology is already there. So why are we bothering? We are bothering because if I want to speak to Siri, Alexa system to my phone to get instructions, the system can read a series of guidance on pathways to follow. But if I have a robot in my home and I would like to have a shared understanding of words with the robot, and I ask the robot, let's say, to prepare a cup of coffee for me, I wouldn't want the robot to give me the recipe the same way Alexa would give me a recipe to make a cup of tea. I would expect instead the robot to make the tea for me, prepare, boil the water, do what it has to do, and then serve me the cup of tea. So what's the problem nowadays if we use an Alexa Siri type system and to a robot? The problem is this, Stephen Harnack calls it the merry-go-round of Amodal symbol systems. And I'll show you why. Let's assume I ask the robot or Alexa to give me the meaning of a very easy word for robots, push. Robots can do very few things, but one of the things they can do is move their arms to push an object in an assembly task. So if I ask what's the meaning of push, Alexa, Siri won't have any problem because they use a dictionary-based knowledge and they will give me the definition in their dictionary push. And a definition, if you were to use the American English Webster Dictionary, push is defined as to press forcefully against to move. Very generic, general definition, but still it comes from our dictionary, so it's okay for us humans. So Eliza, Alexa, Siri are passing the first test. But let's trick them, or let's try to understand really what they mean for words, or what they relate to in terms of word meanings, like in the gavagai context. What's the meaning of gavagai in your own contextualized environment? So let's ask the system again to define another word using the definition of push, which is, for example, force. Force is defined in the dictionary as energy or strength. So Eliza will give me the definition again. So well done, she's passing the test. Now give me the definition, please, of energy that defines force. And energy is defined in the same dictionary as strength of force. You see merry-go-round. The merry-go-round is when you go back to the same point from where you started. And this is not right. So merry-go-round is the play game for children's play parks. So this is not enough. If I continue the examples here, you see lots of merry-go-rounds. This is not satisfactory for a robot, because I don't want the robot to give me definition of tea, hot water, sugar, tray. I really would like the robot to understand pragmatically my context. Again, going back to the philosophy of AI, there is another well-known philosopher, John Searle, who proposed the Chinese room thought experiment. There is a person in the room, locked in the room. The person doesn't know any Chinese language, but the person can match visually characters from written questions, and then he can give us answers. So this person can behave like he, she, it is understanding language, but in reality, we know this is not possible. So we don't want the robot to be a Chinese room experiment set up. We would like the robot to understand language. So how do we do this? Our specific approach is to look at bio-inspired or cognitive-inspired approaches to robotics and AI. That is, why don't we look at the way children acquire language? And first, children are not given by nature, by evolution, the full dictionary like bees. Bees are born with an innate communication, simple communication structure. Children, you know, we don't know any word. There is no starting word for us. So we are slow. It takes 18 to 24 months to acquire a few tens of words. Of course, there is something later called vocabulary spurt that allows us to be efficient at learning new words. But for the first few words, it takes months and months of repetitions. Second, children are not sent to school sitting on a desk to learn the language. They learn the language by physically and socially interacting with their peers, with their tasks. And you will see an experiment in a moment in which Linda Smith in Indiana and colleagues have analyzed the body contribution to understanding and learning a language in the early stages. And then if we look at the way the brain processes information, we know the brain is modular. We have visual cortex separate from auditory cortex, but Muller and others have shown that even if you perform a pure linguistic task, the parts of the brain that are active relate to the meaning of words. So they use experiments with words like kick, lick, and pick, and the motor cortex related to the pick, hand, lick, tongue, kick, leg are actually active when you perform a pure lexical decision task. Tell me if this is a word or not. And then later you will see at the end of my talk, children learn in a social context, and they also develop a theory of mind of other people's beliefs and thoughts, and then of course can decide who is a good, trustworthy speaker or teacher for me to learn my local language, or who is not. And again, let's relate this towards the end of the talk to see how we can put all this together. So this approach that you see here, looking at psychology and modeling psychology, it's the field of developmental robotics, or more generally, cognitive developmental robotics. This is a highly interdisciplinary approach where you need a computer scientist, which would be me, let's say in this case. We collaborate with people that build robots, the real roboticists, mechatronics people. We collaborate with linguists, the Rosetta Stone is there, to tell us about theory of language structure, in particular cognitive linguistic approaches. And then of course here you are, at least our colleagues from developmental psychology, we work, you will see in the next slides, we collaborate to do joint experiments to make sure that our models are constrained on known cognitive development phenomena. And of course, we have done past other work with neuroscientists and language learning in animals in terms of modeling also. Let me do a bit of self-advertisement, if you don't mind. So 5 years ago, together with a colleague from formerly Southern Illinois University, Matthew Schlesinger, we wrote the textbook in the field, which summarized all this knowledge in the field. And to make it a bit more relevant to our community here, there is a paper published a year ago, I think, in Child Development Perspective, where we specifically discuss how psychologists can benefit in collaborating with developmental roboticists, which is us. Then for the wider public, there was a March 18, a cover article on our work together with other people working in the same field of self-taught robots or robots that learn like babies. Now let's go into a set of examples. The talk is structured into 3 parts in terms of examples. First, how do you learn words, individual words? Then for concrete examples, colors, object shapes, objects that you use in, let's say, the real world. Then we look at words for abstract concepts like numbers, like spatial prepositions. And then at the end, we look at trust and theory of mind, their role in building robots that communicate and interact with people. In particular, here we stress the importance of an embodiment approach to language, or grounded cognition, if you want, which means that the way you use your body, it's actually important and it helps you to acquire language. Now, when I give a talk to developmental roboticists, non-psychology audience, I show this chart that shows the milestones with some seminal papers on different stages in the first 3 years of age in terms of cognitive development related to language learning. So first year is about phonetics, discrimination, second year, category learning, perceptual organization, of course, vocabulary expert, and then third year, improvement in language production, and then language grammar acquisition, and so on. And what we do, we try to map these milestones into a set of experiments. In particular, you will see we use a baby robot, a child-looking robot called the iCap. This was developed as part of a European project. So it's full European robot. The head is Portuguese. The legs are British, from Salford near Manchester. And the body, most of the body was actually developed between Pisa and Genoa in the north of Italy. And the way we do this, when we implement our baby robot experiments of known child psychology milestones and experiments and experimental protocols, we do this in collaboration with psychologists. So we have started to collaborate a long time ago, 10 years now, with Linda Smith in Indiana, Jessica Horst in Sussex, Floccia and other colleagues in Plymouth, to me, who is now a colleague in Manchester, and more recently, Antonella Marchetti, Milan Cattolica, with whom I'm collaborating extensively. So let's see how we perform these collaborations. Now I'm going to run a video. I don't know about the quality of the video in Zoom, but let's try.
Look what I have.
This video comes from Indiana Bloomington, Smith and Samuelson's lab. It's a mock demonstration of the experiment.
Look at that. Want to play with that?
The researcher manipulates space, left and right. But space means posture movement. The child is not using a high tracker with a chin rest. The child is actively touching, playing with the two objects by to move her body towards the left and the right part of the table. This is very important. This is the main manipulation.
Look, it's a Modi. Oh, it's a Modi.
So the first and only time the researcher names the object, look at name of the object, Modi,
Look at that.
a new word, is when the object is not visible. This is very important. So you show the object, the child engages in some kind of postural interaction and memory, if you want, of the two objects on the two sides.
Can you find me the Modi?
And when you test the child, with the object, of course, now mixed in the middle, you want to show, and this is what they show, that if you do this, 73%, meaning the statistical majority of children, demonstrate that even if the object in step 5 is named when the object is not visible, but the attention of the child and the speaker is on our left side of the table, then the child is able to match the word Modi with the object shown in the same space. Of course, good psychologists will do a series of counter demonstrations. So here, in the first few stages, if you look at the top, the left and right position of the two objects changes randomly. So 50% chance each object appears in each part of the screen. Then you say the word on one side, and of course there is no way, 46% chance behavior, there's no way you can do this. So these, plus other additional experiments, show that the postural attention is important and is used by the child as an extra strategy to learn the name of words when you are actually acquiring this new knowledge. And about 10 years ago, we had, I used to work at Plymouth in the south of England. We had a new robot, a new iCap, and we wanted to start to teach it to speak, to understand the meaning of words, meaning instead of giving me a definition of modi, of an object, the robot has to demonstrate to me that it knows how to use it and it recognizes its visual features, its color, its shape, and its function. So let's see how we did this. Here you are going to see an experiment in two parts. The first part is we model the fast mapping. Fast mapping in language acquisition is when you learn the name of a word fast because you see the object and you hear the object at the same time. And if you are towards the end of the second year, closer to the vocabulary expert, you can do this in one or few presentations. In the early stages, you will need to do more. So here, fast mapping for language acquisition, first part. Second part, Toni Morse, my collaborator, is going to demonstrate the postural experiments like the modi setup.
So this is the ICO robot, and today we're going to teach it the names of some objects. Here, a truck and a ball. So let's see how we go.
So that's fast mapping. The robot sees the object, it hears its name, new object. You can see that Toni shakes the object to make sure that the robot pays attention to the center of the object. And this is the demonstration that the robot knows what the object is rather than just giving you a definition. In other experiments, the object is used for some functions. Next is the demonstration of Linda Smith and Samuelson's experiment, where they manipulate posture while naming the object when the object is not visible.
So when children learn the names of objects, those objects don't have to be in sight. It can be through association. So we'll show you how that works on the robot. So we'll show that object.
This is what the robot sees with its cameras. So pay attention to the robot posture in terms of neck movement. So look at Toni's hand. The robot looks at the hand being shaken. It goes back to the same position where the piano was originally shown. And you can see that even if Toni said, this is the piano when the piano was not visible, the robot has created the association using its posture as a way to map previous experience with the next one. I'm going to skip these slides, which represents the machine learning, the neural networks, artificial neural network behind the robot architecture. I think what matters here for our audience of psychology is that our experiment and our cognitive architecture based on this machine learning neural network can model the different protocols, the different experimental setups. So that you see here in the first pair of columns, these are the data from the robot and the child, similar performance. Above chance, this is the classical setup of the modi. In the second experiments, we don't report here the child data because this was reported in previous experiments. You can see that the robot would replicate the child data. What's more important here is the next three columns, because in these cases, in the first two experiments, we modelers, roboticists, read the papers and built the new robot experiment reading the paper's protocol and results. In the next experiments, it's the other way around. We roboticists created new experiments, and then the psychologists run child data collection to verify, which is the case here, our prediction. Our prediction was that if you add the second dimension, in addition to moving the object left and right, you also move the object up and down, or actually, you move your body posture vertically in two positions. If you do this, there will be, and you move the object in the switch task, you change the object position 50% of the time, there is no way, this is the third experiment, that the robot will learn. We call this the interference task. Also, fourth experiments, if I move the object randomly, and I keep the left-right posture, there is no way it can learn. Instead, this is the most important element. In the final fifth experiment, what we do, when we swap the position of the object to the wrong position, we also move our vertical dimension. So using a second dimension, postural dimension, vertical, in addition to the left and right, allows the robot to stop the interference task happening. this means the robot, and in this case even children, use this additional manipulation to learn words, stopping the interference of the change of position. In the paper, we discussed this in detail. Here, probably I'm rushing a bit, but this is to say that we were able, with our robot model, to predict a new phenomenon in language acquisition, which is if you increase the number of postural dimensions, you can allow the robot to learn 2 tasks in parallel without the 2 tasks interfering, which would be the standard setup. So if you remember, my second slide showed 2 questions that we always aim at. How can I build better robots, but also how can I build better models of human cognition, which is, I believe, the case here. So this was the first example. Collaboration with Katie Toomey and Jessica Horst in Sussex. Classical mutual exclusivity. I don't need to tell you what this is about.
Oh, awesome, thank
So
you.
2 objects are known, one new object, one new word. And here is our robot performing the same task. Here we teach the robot first with fast mapping the word tomato and the word frog. Then we test the robot for mutual exclusivity for this strange object here.
Which is a frog? Can you show me the frog? Frog.
This is the test of the fast mapping. Now let's do the real mutual exclusivity.
Which is the hux? Can you show me the hux?
Look at the robot's gaze.
Yes. Thank you.
So here the robot hands were being repaired. We added the skin to the forearm, and therefore the robot cannot use the gaze as a communicative act, which is very nice from a psychological point of view. Now, these are, again, child data, robot data that shows that if you increase the number of competitors, mutual exclusivity stops working. What Katie Toomey demonstrated is that to explain this phenomenon, you don't really need to require the novelty principles. It's just a matter of exclusivity where the number of competitors is much. And now here, let's look at a narrative where we put together different capabilities in a robot. We call this an open-ended cumulative learning. It's like sending a robot to a nursery school, to a kindergarten. So here we have fast mapping.
Where is the box?
Next, we have mutual exclusivity with just one competitor, very easy.
Where is the statement?
So one competitor, straightforward, the robot knows the new object and the new name. Of course, you don't forget the previous name box. Here we add early grammar, 2 words, color and shape, or adjective and noun, if you want.
What is this?
Red, code.
What is this?
Code.
You can see that we can generalize the property of the shape. Here we generalize the property of color. That's the only feature for which we have a name. And we can continue the experiment. We can teach a new set of pair of words, green and leaf, and then we do more experiments. So this is our vision in developmental robotics. We wish that you give the robot many developmental constraint and based strategies so that it can autonomously, remember the Scientific American self-taught robots. They have to learn by themselves like they would do in a normal situation. Now, I have about 5-7 minutes left, so I'll try to show snippets, short presentation. What we showed up to now, I call it the easy bit. Easy because we have bright colors, big different shapes, so the robot can easily distinguish and name this object. What if I want to teach robots more abstract words like numbers? How do I show one? Because I'm one person, we are one community online. I have one piano, red piano in the experiment. So there is nothing perceptually common. How do we do this? The answer is in these pictures. Developmentally, we learn to count by using finger pointing. We learn to count by using finger counting. Pointing, finger counting, and so on. We develop a mental line that maps space, let's say left to right, depending on our culture, into numbers. So we did the same using our developmental approach. In the left, you see an example of a robot that learns to count using fingers. The next one in the middle, robot points at objects. And these are again modeling well-known experiments. The one in the middle models Alibali and Di Russo's experiments on different strategies of pointing, where the teacher or a puppet are pointing at the objects being counted. And here is an example of the robot counting small numbers up to 10, and also showing the capability to reproduce and also to perform small additions. This is very important. We are not modeling at the capability to add numbers. We are modeling the capability to use fingers to perform this basic finger manipulation task, which later we hope can become part of a real acquisition of mathematical skills. You see, a very good robot. And then here, this chart on the left shows how numbers are similar in the internal activations of the neural network. This is like the internal brain of the robot. So if you look at the finger, the robot can learn to count by saying aloud 1, 2, 3 while it is moving the fingers. You see that 1 and 2, 2 and 3, 3 and 4 are similar. The branching here, low branching, means they are very similar. And of course, 1 is very dissimilar from 10 because you need to go up in the similarity space and then go down, which is good. This is what numbers are about. 1 is similar to 2. 1 is very different from 9 and 10. But let's look at the mind of the robot, or the brain of the robot, that only learns to babble numbers, like Alexa. Alexa, can you count to 10? And Alexa will say 1, 2, 3, 4, and so on. So if you look at the Alexa's mind or activation of the neural network, you can see that there is a total mixing on numbers, and actually the similarity might be about sound. So 7 and 6, 2 and 10, they are sound. There's some similarities, 7, 6. So the S or the T in 210 is probably what makes them similar. But this is not what numbers are about. Numbers are about sequence and similarity in the sequence. And now let me conclude with a final experiment where we add another dimension, which is social interaction. I'm learning from these teachers telling me this is a Modi, this is a piano, this is red, this is number 1, this is number 2, but why shall I learn from every robot? And an important aspect is trust. How do I trust? If I have a robot in my house, and the robot is, I'm old, is here as a social companion, it tells me to pick up, to take my medicines at 11 a.m., why should I trust the robot? That's one direction of studies. The other direction of studies, I'm a robot, you are teaching me a new set of instructions. Why am I trusting you? Are you my master? Are you my owner? So what we did, again, in good old-fashioned developmental psychology, developmental robotics approach, we look at a link in the literature between theory of mind and trust. So this is the classical theory of mind, Salian test. I don't think I need to explain this. It's a cartoon that you run. Older children know that if one of the characters is away when you move the objects in the containers, of course, you can predict the expectation of the other person. And there is a study in Vanderbilt in San Diego, UC San Diego, that shows that trust and theory of mind are linked together. You will see the paper by Vanderbilt be mentioned in the video. So here we are teaching a robot, this is the robot called Pepper. We are teaching a robot to perform this theory of mind and trust task, but instead of using the Salian, we use the Vanderbilt task, which is putting stickers on the left and the right. It's like putting an object, a marble, in one of the two locations. Let's look at the video. Collaboration with the University of Palermo, Antonio Chella. So Vanderbilt paper, linking trust and theory of mind. There are 3 stages in the experiment. First, we need to...
Please look at me.
You play the game with the experimenter.
Can use the chance either location of the sticker, left or right.
And you build the theory of mind or the level of trust of your interactive person.
Right.
So you see, first one was very non-reliable. Second is a good helper. The label here is only for us to know. The robot doesn't know this label. The robot has to build a theory of mind of the different people. So second phase, you know people.
Right.
I have a theory of mind. And I use this to predict your behavior. The robot uses the theory of mind of the person with the red shirt. In this case, the robot meets a new person, and it projects its own knowledge of the social environment.
Sorry.
This is an interesting part, the final bit. So I have a theory of mind on the right of the reliable person. What the robot is doing here, the robot is explaining to the person with the blue shirt, which is a reliable person, trustworthy person, it's explaining why its predictions were right or wrong, using reading aloud the state of this internal theory of mind. This is an important observation because this is now linked to a very hot topic in robotics and AI, transparent, explainable AI. If you give a doctor a powerful AI system to help identify cancer in the skin by looking at the picture, you want the robot or the AI system to tell you why it is predicting specific problems, medical situations, rather than just trusting the robot 100%. So to increase trust, we need to have robots or AI system which can explain the way they achieved their behavior. But now I have the final slide to conclude my talk with a series of take-home messages which I would like you to remember. So first, let's look at the achievements, positive aspects. We use an approach which we call human-centered AI and robotics because the person is at the center of the system. First, as a user, we do experiments on human-robot interaction for trust. And second, because we use these bio-cognitive inspired approaches from developmental psychology. We stressed the importance of using and exploiting your body, the fact that the robot has a body, to help it to learn better. Like a child exploits its postural attention in the Smith and Samuelson tasks to learn words even when the object is not visible when it's being named. You saw that we can combine multiple phenomena in the same experiment. When you saw the video where we did fast mapping, mutual exclusivity, two-word combinations to allow the robot to acquire its competence. And then in some experiments, we can actually perform a direct mapping between results from experiments, different experiments in robots, and results from different experiments with children. So what should we do, or what are we doing really? Some of the open challenges are, the first I showed open-ended learning, the robot that can learn cumulatively many tasks, but our robots are almost like 2-year-old infants in the sense that they can only understand 10 words, 20 words. An older child would understand 1,000 words. So are our machine learning algorithms powerful enough to handle larger, more complex dictionaries? I mentioned, of course, the importance of explanatory AI for trustworthy robots. To improve trust, you need to improve explanations. And if you have a robot making you a cup of tea, you want to know when the robot makes mistakes so that you can teach the robot to make a better cup of tea by asking the robot explanation about its strategies, just as a matter of example. Then another line of research, which I couldn't present here, is that we are modeling more realistic brain architectures. The cognitive architecture behind these robots are always artificial neural networks based on constraints of human brain structure in a very high level way. In studies, we are modeling individual spiking neurons involvement in this kind of embodiment tasks. And then finally, why do we do this? Remember, I have to wear my computer science hat because I work in a computer science department, so I need to look at applications of our developmental robotics research in addition to the psychology relevance, which is the case for you guys. So in this specific case, the way we do look at relevance is by building experiments of robots which act as social companions for older people, or robots that also act as tutors, helpers, teachers' helpers in language learning tasks, for example. Let me conclude by reminding you that we go around, or in this case, we just stay home giving Zoom presentations, but when the lab will reopen, the clever and lovely students that you see there are the ones really doing the hard work, which I have the pleasure of presenting. And I can stop here, passing the word to Toni. Thank you.
Thank you, Angelo. That was fascinating. I am so impressed by the potential here of what robots can do and what they might offer in the future. Let me remind everyone that we now have our open-ended question time. I invite you to write questions in the chat box, although I see we have a question and answer, but for some reason people recommend that we use the chat box. Okay, so let me begin as people think about what kinds of things they might want to ask you about. So I worry about the balance, and I noticed in your final comments you talked about the challenges and the opportunities. I worry about the balance in the sense that I once saw this video called Selling Your Soul, I think what it was. It was a high school teacher who ran an experimental class, and to come into the class, everybody in the class had to agree not to use their cell phones for the whole semester. And then they kind of tracked the withdrawal. And there were lots of examples, but some of it was really stunning. And that people just were losing the skill of interacting with people. So, I mean, one of the things was one woman said, if I can't order my pizza online, I just go to a different place because I'm not going to phone anybody. I don't want to talk to anybody on the call. And another person said, you know, I was so surprised at how different it is when you look at people in the eye when you talk to them. It was really interesting. So anyway, you see where I'm going with this. My question is, I really don't think and have no interest in pulling back the progress we're making with robotics. But my question is, how are we going to deal with this robotic human interface and help with what I see as the increased inability for some people to interact with real people?
Yeah, very good comment, Toni. Hard to answer, but I have a few sub-answers.
I bet you do. I bet you've thought about this.
So first important questions. When we run our human-robot interaction experiments, of course, we follow our ethical procedure. Plus, in any project now, we have a user panel, which in some way leads us to choose or not specific applications. So the user involvement in the different stages is helping us to make sure that we do what users need. Of course, what the users ask us to develop must still have non-positive consequences. So one way to handle this is to run experiments to understand. So this is exactly what we do as university. We don't sell products. You know, we build prototypes to understand how humans react to this, and our knowledge of this will help us to build better human acceptable robots. So in some way, the final video on the trust is our understanding of how robots can improve trust. At the same time, this means if I think that we shouldn't build a robot that tricks all users and everybody believes it, so that's one way to manipulate it. We know social gaze, the robot gaze, is very important in increasing trust, so we could manipulate this. And the third element is that less young generations,
Well said.
you know, we have to accept that we are dealing now with the new generations of babies using iPads. One day might be baby exposed to robots. So together with educational psychologists, and others, social psychology, we need to make sure that we provide as a society, guidelines and allow the right things to happen with a high interdisciplinary approach. There is always a risk with any technology, but the technology is coming, it has potential positive outcomes. Let's make sure that we work towards this potential positive together, different groups from different disciplines.
Yeah, I completely agree. I mean, this is a great benefit, and as it has enormous potential. And I think we have to, you are a great example, because often the problem is you have people who work in robotics and people who work with children, and they don't, or people of any ages, and they don't talk to each other. I once worked with a team here at the University of Michigan where they were creating a companion robot for older people. And we were planning a 5-year plan, and I said to them, well, when are you going to try this out on old people? And it had never occurred to them, which is, so basic for most developmental psychologists to talk to the people you're studying. They were just very focused on the machine part of it. So I think we have to get what you're doing, the kind of interaction of the two. And I think we have to find a way to do both. I have a question here. I must tell you, I think we have a way to get this to you, but there are many, many, many congratulations in the chat saying what a wonderful presentation. The details were amazing, and they loved the fact that it was interdisciplinary. I have here a question. Let me see if I can show it. Have we lost Angelo? Frank?
It does look like he's not here at the moment. There was a little internet connectivity problem. Well, as soon as I see him pop up again, I'll promote him.
All right. Well, I won't read his questions. I will read his questions. So he says the robots can memorize a few words like.
There he is. He's back.
Angelo, are you back? What happened to you? We missed you.
I think my home connection went down for a while, so
Yeah.
good timing. Sorry, not good time for the questions, but at least for the talk.
Yes, at least it was there. Okay, so I was starting to repeat for you a question that we got in the chat. It says here that the prof says that robots can learn or memorize few words like a 2-year-old, but at the same time, the prof says you can ask them to make tea. I missed something here. So robots can understand abstract words better than children?
So not better than children, no way. So we are trying to model or to understand how much we can stretch our algorithms to reproduce non-human-like, to go towards human-like. So our robots can only handle 10 words, and the robots are not capable, just to clarify, to make a cup of tea. It's an example that I use just because I like tea. I'm Italian, but maybe that's why they send me to England. I like tea. I don't like So I use this example. The example is really to say that we would like the robot to use the words to make things, not just to give me definitions. So I'm not sure I understood the questions fully, but we model early acquisition because that's the only thing we can do. It's easier, of course, to model a child than not to model a fully language native speaker, let's say. The challenge is to show that our algorithms are capable, with more research, to handle the complexity of the human language. And if you ask me to bet money on this, I will bet some money, but not too much, in the sense I know the limits of our. And this is also positive. This answers indirectly Tony's first questions. Progress in robotics is low because we are dealing with very complex challenges, building human-like capabilities. Therefore, it will take years to build robots that can do our things. So I would like to reassure people that robots will not steal our jobs, in the sense that robots can only do repetitive tasks. A robot nurse will not exist in my lifetime. A robot which can help in a COVID, to make it better, in a COVID a word to do some monitoring, this is possible. The robot that will substitute humans fully is not possible in my lifetime, which is a good thing, I would say.
Well, I think we have to go with that it's not a matter of substitute, but it's a matter of complementarity to free the human to do the more complex behavior. So we have a question from a linguist who says, I do agree that postural behavior is very important for a child to learn new words and also to learn them faster. It is a kind of stimuli, but what kind of interaction at a classroom with more than 50 children?
You mean how you can extend this? One of the benefits, I'm involved in a new project led by psychologists, Mila Vulchanova from Trondheim in Norway. This project is about looking at the way children can use technologies, iPads and robots and other digital technologies to help children develop language skills, both for normally developing or children with learning disabilities. So in this case, we see the role of the robot more like a teaching assistant. The teacher will handle the complexity of the interaction in a classroom in a large group. And then you can imagine, I give my, we're talking about blended learning now in this new era of COVID, okay? So I teacher, give the children my main lecture, and then I can do my parallel Zoom rooms, or if you want my parallel robots, they will do one-to-one tutoring. So that's one way the robot can play a role, I think, in this context.
Yeah, that's nice. I think we should be creative about that. There's a lot of potential. So we have a question, a very developmental psychology question. Have you taken into account the influence that this robot could have on learning of a child who is growing up with it?
I mean, not personally, but of course this is very important. I use the metaphor of the iPad. The iPad is changing the way children interact with the world, with the knowledge. Let's be honest. We started when we were young psychology students reading the book of abstracts to do a literature review of what was the name? Psych abstracts.
Psych abstracts.
Yes. So we don't do this anymore. We just Google, right? So
right.
We have changed. This iPad generation, iPad in the sense, tablet, has changed. So the new generation of robotics is changing. There are groups, of course, they are looking at more educational aspects of robot. So this is an important area of development, not my specialization, but clearly something to do, to understand what changes, how does it change the way children learn?
I know this sounds a little bizarre, but I think about that, that movie called Castaways. I mean, it had nothing to do with robotics, but he became very attached to that soccer ball, and you could watch the development of that relationship. It was very bizarre, and we have in the past had studies of attachment to inanimate objects. So I think this question about
also,
how you
our children's generation attachment to their YouTube on the phone or Instagram is similar, if you want. We couldn't remove a phone to a child. Actually, you couldn't remove the phone to me because I'm also phone dependent, smartphone dependent.
I know,
So,
but I mean, talk about new forms of punishment. You take away a phone, it's like the worst.
the worst. Yeah.
My own grandchildren, I'm amazed with their attachment to their iPad. And there are many wonderful educational opportunities. The other day, my grandson was telling me about playing math tango, and I had never heard of it. And for a long time, I couldn't get the two words together, math tango. And he's only 4 years old, and he didn't really know that he was learning anything. He just thought it was a game. So I think there are great potentials there. And especially while parents are doing all the homeschooling, it has a lot to offer. All right, before we go on, let me ask this question. One person asked, could you make, they didn't quite get the connection between language acquisition and trust, or theory of mind. Can you speak a little bit about that?
So, thank you. the example I showed only linked trust and theory of mind. So Vanderbilt runs a modified Sallian task with the stickers to show that if the child builds a theory of mind or the expectation belief of the other participant to decide how to trust social people. This is the non-language context. Another paper, which I didn't present here for brevity, we ran the same experiment that you saw at the beginning, the robot interacting with the MODI setup where you show objects and you name them. And here we manipulate the theory of mind. You have two teachers. One is reliable, one is unreliable. And again, this is a study run by Harris and Koenig that demonstrated that you can link theory of mind and trust in a language learning task. So I couldn't focus on this, but there is a paper, Koenig, Harris, or if you look at I have a new paper that describes this in detail, Patacchiola, Cangelosi. It's impressive, it just got accepted. So it wasn't in my talk, but it's related.
What journal is that in?
No, the Koenig Harris, I don't remember it at the moment. I will need to look at my slides. I don't know what follow-up we have here. So email me and I can give you the reference.
Okay, great. All right. So actually, here's a very interesting question. This person says, we only have time for a little bit more. This person asks, she would like to know the place of culture transmission and whether the robots are built in specific cultural contexts.
If you use the language learning example, sorry, the number learning example, we know the finger counting varies across cultures. In particular, it's linked to the direction of reading, for example. We count left to right, or we read left to right, and this changes in different cultures. So we have done a small study of a multicultural robot that is trained to count, finger count in one direction, and then swap it. So it is possible to manipulate this, at least in these cross-cultural studies. We have done some toy examples of this, but this is something that you would consider. If you think word order, when you do these language learning experiments, you impose a word order. Word order is, language specific, and you could manipulate this as an example.
Oh, those are very concrete examples of culture. I suspect this person meant culture in the broader context. Broader context and the more subtle context. That's tricky.
Operationally, I would need to map this into, in an experiment with a robot, I would need to operationalize this into a concrete example. This is why we simplify this into.
Yeah, this is just such a fascinating example of how you kind of link the engineering robotics approach to the developmental psychology approach. And I think it's doable, but you're right, you have to think about it carefully. Here's one question, I'm not sure I understand it, but hopefully you will. The person says, if I understood correctly, you consider domain general theoretic frameworks, for example, Piagetian stage-like frameworks of development as an assumption for the learning of the robot. Have you considered domain-specific theoretical frameworks for teaching the robot? Are there specific technological preconditions that need to be met for domain-specific theoretical frameworks? And we have 1 minute left, so offer what you can.
So my quick answer is that practically we are following, of course, a Piagetian, Vygotskian, if you want, contextualized approach to modeling developmental cognition. Of course, our approach could be used to test different hypotheses by manipulating the input to the robot or the context of the task and so on. But we are not doing this currently, but it is possible in principle.
Okay. Well, I thank you very much. This is fascinating. I feel like I've entered a whole new world to understand, well, to begin to understand, but certainly the potential here is enormous. And I think it's our future, to be quite honest.
You.
Okay, thank you. Hope to see you next in 2022, hopefully in Rhodes.